13.7 billion years ago, this was the entire universe. There was no matter, no atoms, no light, nor sound, only pure energy. But that was about to change. This is called the Big Bang, the beginning of everything. Now, let's pause again. 1 picosecond after the Big Bang, it is 10 to the 15 degrees right now. If you see this written out, that's 15 zeros. It is so intensely hot, the energy of this early universe spontaneously converts to matter. Matter and antimatter are created here, and then when they touch each other again, they are annihilated, converting back into the energy that created them. As the universe expands, cools down. Let's pause again 1 microsecond after the Big Bang. It is now 10 billion degrees and we're in a universe full matter and antimatter. These matter are quarks, the smallest known particle. The high temperature prevents them from combining, but eventually the temperature lowers enough for 3 quarks to stick together, forming a proton. It contains 2 up quarks and 1 down quark. If instead you combine 1 up quark and 2 down quarks, you get a neutron. 1 second after the Big Bang, the universe cooled further. If we check what is present in this universe, you must notice something strange. There's no more antimatter. Matter won the fight against it. We're now in a world, protons and neutrons. 10 seconds now. If you check, you will see that there are more protons than neutrons. This is because neutrons weigh slightly more than protons. Now, look at Einstein's famous equation and remove the c² part. And then you see mass is energy. As neutrons weigh slightly more, they need more energy to be created. And they can change into a proton by losing some energy by expelling an electron. Because of this, there are now 7 protons for every neutron. Skip ahead to 3 minutes after the Big Bang, and now it cooled enough for the protons and neutrons to combine. Proton on its own is hydrogen. Next, it can combine with a neutron to form deuterium. By adding another neutron, you get tritium. If you instead add another proton, you get helium-3. It's much easier to add protons to deuterium than to make that deuterium in the first place. All the deuterium that's formed gets used very quickly to form helium-3. It's called helium-3 because the sum of the protons and neutrons is 3, and everything with 2 protons is helium. If 2 of these helium-3s collide, 2 protons bounce off and helium-4 remains. Again, 2 protons means it's helium. Helium-4 is super stable, so those protons and neutrons are very happy here. If you add another proton here, you form lithium-5. The protons and neutrons are a lot less happy here. When this happens, a proton is expelled to form helium again in about 400 yoctoseconds. In case you have never heard of a yoctosecond before, that's 400 times 10 to the minus 24. This is what it looks like with the 24 zeros spelled out. Even in a 3-minute-old universe, this happens in an instant. If instead 2 heliums collide, you form beryllium-8. Beryllium-8 falls apart in about 10 to the minus 17 seconds. 17 zeros. Helium is so stable, it rather stays helium than either lithium or beryllium. Now, remember tritium, which is hydrogen with 2 neutrons. If this collides with helium-4, you do get lithium-7, which does not fall apart, but tritium is not very abundant. 20 minutes now. It's now too cool for any more nuclear fusion. The universe is now 75% hydrogen, about 25% helium, and a small amount of deuterium, helium-3, and traces of lithium-7. That's the whole universe now. Normally, electrons circle around the atoms. However, here, the temperature is very high, and because of this, the electrons have a lot of energy. So much, in fact, that the protons cannot capture their electrons. The hydrogen and helium atoms are swimming in a sea of free bouncing electrons. Now, if you skip ahead to 1 year after the Big Bang, nothing much has changed. Still, only hydrogen and helium floating in the sea of electrons. 10 years, same picture. 100 years, and you'll still observe the same atoms floating around with electrons bouncing everywhere. 1,000 years after the Big Bang, you guessed it, everything is still the same. It took 300,000 years. It's now about 5,000 Kelvin, and the atoms can finally capture their electrons. Only now do we see the atoms like we see them here in the present. It is also during this recombination that the cosmic background radiation was released. 1 million years after the Big Bang, and we are entering the dark era of the universe. The hot matter from the early universe glows like a hot iron glows due to its high temperature. The early universe used to be orange, but now it's fading to black. 10 million years after the Big Bang, and everything is dark. There is no source of light here. If you were to visit this era as a time traveler, you would see nothing at all, pure darkness. And this is going to last for a while. Our matter, the hydrogen and helium atoms, are spread almost equally in the universe. Almost. Some regions have slightly higher densities than others, and due to gravity, these slightly dense regions attract more atoms towards them. As time goes on, more and more mass clumps together, increasing the density and causing gravity to attract even more mass. This process has been going on for tens of millions of years, with more and more matter accumulating in the higher density areas. As more and more matter is pressed together, the temperature and pressure increases and increases, and once the temperature and pressure are high enough, nuclear fusion is possible again, and it ignites. 300 million years after the Big Bang, the first stars appears, bringing light and ending the dark era. The era of galaxies begins, but these are no ordinary stars. These are red hypergiant stars. These early stars have masses thousands of times that of our Sun. In the early universe, just after the Big Bang, helium is made by combining neutrons and protons, but now all neutrons are already stuck in the helium atoms. In order to make more helium in the core of the star, two hydrogens or protons have to be combined. At high temperatures, when two protons collide, a positron forced out of the proton. This positron is the antiparticle of the electron, with a positive charge instead of a negative charge. This takes the positive charge out of the proton, leaving a neutron behind. This neutron combines with a proton to make deuterium. Unlike the creation of helium after the Big Bang, which lasted just minutes, this process lasts a long time. The larger the star though, the faster this hydrogen is consumed, though it's never really that quick. For our Sun, this process lasts 10 billion years. For these gigantic hypergiants, it will still last several million years. In a star, there is a balance of forces. Gravity presses everything together, but the nuclear fusion inside the star exerts a force outwards. This is why the size of a star is stable until the hydrogen supply becomes too low. The outward force can then no longer hold off gravity, and everything is pressed together. The star then collapses, and this causes a supernova. Not all hydrogen is consumed before the supernova, so after this explosion, hydrogen is spread out again. Gravity brings this together again, but now it's no longer only hydrogen and helium. Heavier elements were produced in the star and during the supernova. As this cycle continues, new stars with more and more heavier elements are born. 1 billion years after the Big Bang, the universe looks a lot like the present universe, except that the star formation is more active. The heavier elements produced in the first cycle's stars allowed the formation of planets, asteroids, comets, and other stellar bodies. 9.1 billion years after the Big Bang, a very familiar star is formed, our Sun. The material inside it has resided in countless stars before. Around it, many rocky bodies were formed, using the heavier materials such as iron, silicon, and oxygen produced in former stars, made from literal stardust. This is early Earth